Okay, so hi everyone. Today we're going to be looking at different ways to interpret the standard deviation in statistics. So, first of all, we're going to look at two really important rules that will help you know how much of the data set is contained within certain intervals. So, this is going to make sense in just a minute. So, first, we're going to look at Chebyshev's rule. There are a lot of Russian names in statistics, so I'm sorry if I'm mispronouncing this. But this rule works for all data sets. So it doesn't matter their distribution or how the data looks like. So this is a general rule for all data sets. So basically what this rule says is that the interval x bar minus or plus 2s contains at least 3 over 4 of the data set. This means 75%. And so let's talk about what this interval means. Okay, so x bar we know is the sample mean or the average basically, and s is the standard deviation. So in the interval x bar or the mean plus or minus 2 units of the standard deviation, we have 3 over 4 of the data set. So this interval contains 75% of the data set. This is what this means. The same for 3 standard units. This interval x bar plus or minus 3 standard deviation units contains at least 8 over 9 of the data set. This translates to, if you just calculate this, it would be 88.89%. So this is 88.89%. So what you really need to focus on in Chebyshev's rule over here is that it's at least 3 over 4 and at least 8 over 9. So his rule is general. So over here we're saying that there could be more than 75% of the data set within this interval or more than 88.89%. But we just have like basically a minimum, which are these percentages. And then it just has a very general rule that it is possible that the interval of the x bar plus or minus 1 unit of standard deviation contains very few of the measurements, but we don't actually have any or specific percentage. In general, though, the way you can remember this, because you might forget like this rule with this rule, because usually on tests, these rules or bullets are not given. So a way to remember this is this really important last line over here. So in general, the interval mu, which is the population mean or population average, minus k is a constant, okay, k is any constant, and sigma is the population standard deviation. So this interval, regardless of how many units, so regardless of k, contains at least, and this is the formula for the fraction that we keep getting over here, 1 minus 1 over k squared observations, given that k is greater than 0. So obviously k can't be 0 because then this would be undefined. And yeah, so basically it says that if you have k and you have mu and you have sigma, you can easily tell the at least what percentage lies between this interval. So we're going to put this into practice in just a minute, but this is a very important rule to talk about. So for this rule to be applicable as well, k has to also be greater than 1. Why? Because if you plug in 1 over here, it's going to be 1 minus 1, which is 0. So you're going to be saying that the data, that this interval contains at least 0 observations, which is very useless information. So starting from 2, you can really tell. So for example, it's going to be, if k is 2, then we're just going to do 1 minus 1 over 2 squared, which is 4. And then you get 3 over 4, which is the 75% that we already have over here. So if you fail to memorize these, this is a general rule that will help you regardless of the k. For example, if you have k equals 4, so you don't know it from these 2 bullet points, or k equals 5, so you're going to be able to solve any problem using this. Next, we're going to look at another important rule called the empirical rule. And this one is less general and more specific. So we said that Chebyshev's rule applies to all data sets or all distributions. However, the empirical rule only applies for mound-shaped frequency distributions. So basically, if it's approximately a normal distribution or follows a normal shape like that, or almost like that. So over here, if you noticed, okay, we're talking the same way, same everything, same notation, x bar minus s, x bar plus s, so plus or minus 1 unit of standard deviation approximately 68% of measurements fall within one standard deviation of the mean. All right. For 2, it's 95%, and for 3, then all the measurements fall, essentially all of them, but we like to denote this as 99.98% of the measurements fall within the 3 standard deviations of the mean. So this is really useful. It gives you a more precise and accurate interpretation of your data if it is mound-shaped or normal-shaped distribution. So you need to make sure that this condition holds true first. So over here, why is this better? Because here we're saying approximately, this is the exact percentage, approximately. However, in Chebyshev's rule, we are talking about at least. So we're just talking about a lower bound, basically. We're not really talking about the full picture or exactly what these percentages could be. So there isn't really a general formula for this one. You can just memorize it as the 68, 95, and 99% rule. To just remember that it's one standard deviation of the mean, 2 and 3, and you just memorize 68, 95, and 99.9. So we're just going to solve a couple of problems to see exactly how those rules are applied. Okay, so over here, you are given this question. A distribution of measurements is relatively mound-shaped with mean 50 and standard deviation 10. So over here, this is a really important keyword. They said that it's relatively mound-shaped, so you know that you could use the empirical rule. And it mentioned that the mean or x bar or mu is 50, and the standard deviation or sigma is 10. So it's asking what proportion of the measurements will fall between 40 and 60. So the way you solve part A over here is you just plug in your formula. So you know that it's mu minus the constant times sigma is equal to 40, because this is your lesser number, so that's going to be minus. And you also know that mu plus k sigma is going to be 60. So over here, you just plug in your givens. So mu is 50 and sigma is 10. So you get 50 minus k times 10 equals 40. And you just do like really simple and basic algebra over here. And you get that k is equal to 10 divided by 10, which is 1. So given that k is 1, you know that it's when it's 1 standard deviations away from the mean, and this is empirical rule, then you know that approximately, we're not saying this is the exact same thing, so you need to really pay attention to these keywords. Approximately 68% of the data lies within this interval. And you can check the same you'll find that k is also 1 for the addition part of the interval. And then you just do the same for parts B and C as well. So for example, B is asking what proportion of the measurements will fall between 30 and 70. So you do the exact same thing, 50 minus k. We want to know k now because that's the variable basically that we're trying to always find, and it leads us directly to the answer. 10 equals 30 this time and not 40. So you're just going to do 50 minus 30 equals k, but divide this by 10. So this gives you 20 divided by 10, which is 2. So 2 standard deviation units away from the mean, we learned is 95% of the data set through the empirical rule. All right, and then you just do the same for the others as well. Now, we're just going to move on to another example. So a data set of mean 75 and standard deviation of 5, you know nothing else about the size of the data set or the shape of the data distribution. So this last bit over here is just extra explanation, but you should know on your own that when they don't mention that it's mound-shaped or normal distribution or approximately symmetrical or any of these equivalent keywords, then you cannot use the empirical rule. But instead, what you have to use is Chebyshev's rule. So applying Chebyshev's rule and knowing that the mean is 75 and sigma is 5, then you just plug in. It's the same thing. So what can you say about, so the method of solving is the exact same. What can you say about the proportion of measurements that fall between 60 and 90? So you just do 75 minus 5k is equal to 60. And then you solve for k because we want to know how many units away from the mean it is. And then you get k is equal to 3. So From before, if you had memorized, you would know that k equals 3 means 88.89%. But let's say you forgot this, then you can apply the general rule, which is always much easier, and it's advisable to just know that one rule. 1 minus 1 over k squared gives you at least how much of the data set lies within this interval. So over here, k is 3, so this would be 1 minus 1 over 9, which is 8 over 9. So that's approximately 88.89%. So it gives you the exact same thing as to like if you were to memorize the actual value. So 88.9%, make sure that it's at least. So for example, if this is an MCQ exam, they could ask you at least 88.89% or approximately 88.89%. So you really need to know the difference between both. So every time you use Chebyshev's rule, you have to mention at least. Every time you use the mount-shaped one, you have to say approximately. So moving on, I want to talk about two really important measures for relative standing or measures of position, basically. So we're going to talk about two measures, z-scores and percentiles. So the z-score is a standardized score for an observation x, and it's defined by this equation that I'm going to give you right now. So z or z is equal to x minus x bar over s. What this helps you know is the relative standing of your observation to basically the average. So is it normal or is it an outlier? Where does your observation stand? So x is basically your observation, x bar is the average or sample average, and s is the sample standard deviation. So over here, given this really simple formula, it's really easy to memorize, you can just apply it to know whether something is an outlier, an observation is an outlier or not. So the question says body temperatures of a healthy human children have mean 98.60 degrees Fahrenheit. So you know that x bar or mu is 98.60. It's always nice to just like write your given on the side to know where you're standing. And standard deviation or S is 0.62 degrees. Your child has a temperature of 101 degrees. So what should you do? You want to know whether you should take him to the doctor or whether it's normal. So over here, this is your observation, this is your X. So you just plug in the formula, find the Z-score. 101 minus 98.60 divided by 0.62. This gives you 3.87. So you're going to say, okay, how am I supposed to know like whether it's an outlier or not? Basically, for it to be normal, it has to be between -3 and 3. If z is greater than 3 or z is less than -3, then it's an outlier. Then your observation is an outlier. Given that 3.87 is greater than 3, then this is an outlier, so you have to take your child to the hospital, or like basically this is not a normal value for the human body temperature in this example. So these scores are really easy but really useful at the same time to know whether your observation is an outlier or not. Another important measure for relative standing are percentiles, and maybe you've heard of the word before but you don't really know what it means or its interpretation. So if you've taken a SAT score before, they would tell you that in your score report that you're at the 80th percentile or the 95th percentile, meaning that you scored higher or equal to 95% of the test takers within the same year, basically. So the pth percentile of n measurements is the value such that p% of the measurements are less than that value, and the rest are greater than it. So when we talk about the 95th percentile, we talk about Q1, or basically the first quartile. 50th percentile is the median, or the second quartile, which is also Q2. And 75th is the upper quartile, the third quartile, and it's Q3. So these are all just different names for the same thing. So if they tell you what's Q1, they're basically asking for the 25th percentile. If they tell you what's Q2, then they're telling you that's the 50th percentile or the median. Same with Q3 and the 75th percentile. So again, just to reiterate, 75th percentile means that if we're talking about scores, for example, then 75% are less than or equal to this value or this grade or this score, depending on what we're talking about. So how do we find these values? Or like, basically there are simple formulas to know their position. So if we have a data set, and I'll show you this in just a minute, Q1 or the 25th percentile is 0.25 times n plus 1. So n is the number of observations that you have. So you just apply this formula and it's not going to give you Q1. It's not going to give you the value of the 25th percentile. It's going to give you the position. So this is really important to note. It's worth noting 100%. So it's just going to give you the position. So you're going to go check that position, and then that value in that position is going to give you your Q1 or your first quartile. Same with Q2. If you want to find that, you just do 0.5 times n plus 1. That's going to give you the position of your median or the position of your second quartile. And the same with 75th percentile, you just do 0.75 times n plus 1. So it's really simple to memorize. And again, n is just the number of observations. So let's look at this and also discover very important ideas as well that are generally used in statistics. So you have this data set, and we want you to calculate the 5-number summary of the data and a bunch of other things. So let's first talk about what the 5-number summary of data is. So 5-number summary is very basic. It is just minimum, Q1, Q2, Q3, and maximum from your data set. So we have this data set. To get your 5-number summary, the first step you should do is sort your data from least to greatest. So I did that over here. Just put like the least number and then the greatest number. Nothing fancy. And then your minimum is obviously the leftmost one. So over here, our minimum is 2 and our maximum is 22. Then how do we calculate Q1, Q2, and Q3? So we just learned that the position of Q1 would be 0.25 times n plus 1. This is equal to 3.5. So we have 13 numbers over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So n is 13. So it's basically 0.25 times 14, or 3.5. So this is telling me that the position of Q1 is 3.5. What does that mean? I just count 3. 1, 2, 3. 0.5 is over here. So I average these two numbers. So basically Q1 is equal to 4 plus 5 over 2, which is equal to 4.5. So this is your Q1, this is your 25th percentile. So what about Q2? You do the exact same thing. Q2 is basically your median, so that's just 0.5 times n plus 1, and that gives you 7. So the 7th position, or the 7th number, is your Q2. 1, 2, 3, 4, 5, 6, 7, that's 6. So your 50th percentile is 6. And then Q3 is just 0.75 times n plus 1, which is basically 0.75 times 14, because we have 13 data points, and that gives you 10.5. So the position is 10.5, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.5. So that's just the average of 9 and 9, which is 9. So your Q3 is 9. And that's it. You have your 5-number summary, which is really useful, by the way. So now you know the maximum, you know the 25th percentile, the 75th, and the median. So then they want us to calculate the inner quantile range. The IQR, or the inner quantile range, is a very important measure of spread and variability as well. So the higher it is, the higher your spread or variability. So what is IQR and how can we calculate it? IQR has a very simple formula. It's just Q3 minus Q1, two of which we already found. So we found Q3 to be 9 minus 4.5, which is Q1. This gives you 4.5, an IQR of 4.5. So this is a measure of spread. Then you are asked to find the lower fence and the upper fence. So if you have some background on statistics, you would know that right now we're just basically building up to constructing a box plot, which tells you more information about your data. So how do you calculate the lower limit, or the lower fence, and the upper fence? So lower limit, or it's also sometimes called a fence, is just, it has a formula. It's Q1 minus 1.5 multiplied by IQR. So in our case, Q1 is 4.5 minus 1.5 times 4.5. this gives you a lower limit of negative 2.25. And now we're going to see what the point of lower and upper limit is. So the upper limit or upper fence is Q3 plus 1.5 times IQR. So that's simply 9 plus 1.5 times 4.5. And that gives you 15.75. So what this means is that if I have any values greater than 15.75, they are outliers. If I have any values less than negative 2.25, they are outliers. Any values between these two are normal observations. So this is just telling you also a measure of where the outliers are. You could think of it like a z-score basically. So once you have all this, you can easily construct a box plot. Okay, so to construct your box plot, all you need to do is draw like a number line with all the values of your data set. Make sure the scale is right, obviously. So I just did this to just for demonstrating. But in reality, you just have to like write the whole scale. And then what you do is, so Q1, Q2, and Q3, you draw vertical lines for them. So Q1 is 4.5, Q2 is 6, and Q3 is 9. So 4.5, 6, and 9. 4.5 is over here, somewhere here. 6 is here, and that's your median. And 9 is here, and that's your Q3. Okay? And then you just connect these three vertical lines like that. Very simple. And then you look at your minimum and maximum values. But you have to make sure that those two values are not outliers, basically are not outside your lower and upper fence. So the only value that's outside or an outlier basically is 22, but it also happens to be our maximum. So we cannot use it as the maximum value, and I'll show you why now. Basically, you have to look at the second greatest one or the second maximum, which is 10. And you go down, draw another vertical line at 10, like that. And then another one at 2, because that's our minimum. And then you just connect those with a line, the maximum and minimum. And then any outliers, you have to mark them using like a star or any, like sometimes you can even mark them with a diamond. But like the star is what's most widely used. So this is telling me that this value is an outlier, and this is telling me that this is the median, 6 over here. This is telling me that this is the 75th percentile, and this is the 25th percentile, and this is the minimum, and this is the maximum aside from outliers. That's it. And then the width of this box is actually your IQR. So you can really tell if you're comparing two box plots together, which one has higher variability or higher spread, if one box is wider or narrower than the other. The wider the box, the higher the spread, the higher the IQR. You can even calculate it over here because this is 4.5 and this is 9. So if you just subtract that, 9 minus 4.5 is 4.5, which is the value of your IQR. All ideas covered in this video are really important for interpreting the standard deviation. We spoke about the Chebyshev's rule, the empirical rule, the z-score for identifying outliers, as well as the IQR. And yeah, feel free to suggest future ideas for future videos. And thanks for watching.